Okay, so taking a look at a few definitions, and the first one we're going to look at is that definition of at rest, which really means not moving. Now that's not moving relative to a fixed point. Right, so we have a point that we are saying, okay, that is our reference, and compared to that, it is not moving. So for example, this man may be not moving relative to this particular point, but the Earth is still spinning, or the Earth is still moving around. So we just say relative to a fixed point, or fixed point relative to that point, this object is not moving, therefore we say it is at rest. Now, we call this physics principle 0, and where that comes from is on your formula sheet you're going to see this idea of uniform motion. And uniform motion really just means that an object is moving at the same way all the time. So coming back up here, if we were to copy this on page 32, I recognize the fact that many of you do not have this, but you've got a velocity versus time graph, and the velocity is just along here. I'll do this in green just so you can see. And it's staying at, well, 0. Now, uniform motion, right? Uniform motion would be moving at a constant velocity. Again, physics principle 0. The difference in the graphs here, if this is velocity and this is time again, is that a constant velocity might look like this. Now, another way we might draw that would also, if we had time here and velocity, would be, let's say, something along here, and this would just be indicating direction, where that would be the positive direction and that would be the negative direction. Where uniformly accelerated motion, okay, that is your velocity and time. If it's uniformly accelerated, it might look something like that, or might look something like this, but the object is changing velocity at a constant rate. Changing velocity at a constant rate. And everything we're going to be dealing with right now in physics is going to, if you're accelerating, is going to be accelerating at a constant rate. And that is physics principle 1. This one right here. Okay, so we have a few formulas so far, and the first one is that velocity average is equal to the change in displacement over time. There's the acceleration is equal to the change in velocity over time. We've got the displacement is equal to VIT plus 1/2 AT squared. We also have D is equal to VFT minus 1/2 AT squared. We also have the displacement is equal to VF plus VI over 2, with those little arrows multiplied by T. And we've got VF squared is equal to VI squared plus 2AD. Now, a couple of things to note with that. First of all, this formula, because these are squared, we do not consider positive or negative to be direction, because when you square it, you're always going to get a positive answer, even if it's actually indicating negative. So here we do not consider these to be vector values of initial and final velocity. Secondly, the area under curve usually represents the y multiplied by the x. That is your area. If we take a look at a couple of these formulas, well, if we go VF plus VI over 2, well, thinking about this one here, what we've got is a triangle where we have an initial velocity, a final velocity, divided by 2 because it is a triangle, multiplied by the time, the base. So the height divided by 2 gets you the base, or d times v. Right? We get velocity multiplied by time would get you displacement as per this formula here. Now, if this velocity, let's say it didn't start at a specific spot. Let's say it was coming like this, and this was your initial velocity, and this was your final velocity. Well, you could divide up this into two parts, where this would be the 1/2 AT squared, and this is the VIT. Or you could look at it the other way, where we got VF t, which would be all of this, and subtracting the 1/2 AT squared, so meaning we're subtracting this portion. Let's highlight that. Highlight that. Highlight that. So it would be taking away this, where that one would be adding that. And that's the difference between these two. But generally speaking, it really means whatever's on the y-axis multiplied whatever's on the x-axis. And in a velocity versus time graph, that would be displacement. So specifically under first velocity time graph, that would be displacement. Now under an acceleration time graph, let's say that the acceleration in time and it was constantly changing acceleration. Well, what is a times t? Well, a times t, taking a look at this formula, right, that acceleration is equal to delta v over t, which means delta v is equal to a times t. So this would be the change in velocity. What does the slope of a line represent? Well, usually it is the y, change in y over the change in x. Right? That would be the slope formula. And so whatever you got on the y divided by whatever you got in the x. So if we take a look at a position time graph, position time, well, that would be position divided by time. Well, what is the position divided by time? Right? That is the change in displacement over time. That is your velocity. Right? Which is equal to the change in position, displacement over time. On a velocity time graph, well, that would be velocity divided by time. Well, that is acceleration. Right? Which is equal to delta v over t. So depending whether you got a position time graph or a velocity time graph, the slope, and we're talking about the slopes here, will represent velocity and acceleration. Now, if a graph has multiple parts, we always just essentially treat them in each section and then combine them at the end. What do we mean by that? Well, let's take a look at this example here. We've got a velocity time graph, and we've got a few things going on. First of all, between here and here, it is at rest. Here it is accelerating. Here we also have acceleration. And here we're moving at a constant velocity. But if we want to find the overall displacement, well, that's the time multiplied by the velocity. So what we need to do is multiply by the time by the velocity. That's area underneath the curve. But we've got three areas. We've got this one, this one, and this one. Make that a 3. So we're going to treat them all individually, finding the area of these three shapes. Well, let's do number 1 first. Well, if that's got a base of 2 and a height of 8, and it's a triangle, so area is equal to 1/2 base times height, or 1/2 times 2 times 8, which means that we'll have an area of 8 meters. Number 2 is a rectangle with a base of 4 and a height of 8. So A being 4 times 8, that gets you 32 meters. And part 3, it's actually a reflection of part 1, and so it's 8 meters, where it's got a base of 2 and a height of 8. Divide by 2 again. That gets you a total of 48 meters displacement over the 10 seconds. Right? We took a look at each piece and added them together. So if we wanted to sketch a position time graph, right, taking a look at the displacement, well, the first 3 seconds would be at rest. Then we are accelerating, which means the displacement is then moving up. We have a spot with a constant velocity, and then a deceleration down, but we're still moving in the forward position, and so it would look something like that. So you've got your 4 sections, 1, 2, 3, 4, where number 1 is at rest, number 2 is accelerating, number 3 is at constant velocity, so we've got that slope there, and number 4 is decelerating. It's a curve, or negative accelerating. If we wanted to draw an acceleration time graph for that, well, there's only 2 sections which is accelerating, number 2 and 4. At spots 1 and 3, it's moving at a uniform motion. So in acceleration versus time, the first 3 seconds would have no acceleration. And actually, just for simplicity's sake, let's do this with a top and bottom, where this is the acceleration, this is the time. The first 3 seconds, it's at 0. Then it's accelerating in the forward direction for 2 seconds. Then it's at 0 again, and then it's negative. And so we got the 4 sections, and sometimes you can even put in like little dots here, because essentially we've got instantaneous changes in acceleration according to the graph, where it's at rest, accelerating forward, moving at a constant velocity again, no acceleration, and then moving at an acceleration in the opposite direction. Okay, hope that helps you. There are the 1.4 questions. If you do have any questions, give me a shout.